We're good? Sound is moving okay? Okay, everyone. It's a huge crowd today, so I'll discuss the results of the midterm survey. I used this information. I think it's very useful. Still, it looks like not everybody took advantage of the 5 free points, because I think you are 94, and there's 5, 6 people more that didn't want to do it. But the survey is closed. And so I think I just look at these results. What I really usually do is look at the averages, and I kind of get worried when I see something below 4. So this is my grade. I mean, this is the grade that you guys give me in the middle of the semester that is not part of UF's procedures, but it's for me to understand how things are going. And then there is the last one, which is, as you know, it's the actual evaluation of the class and the instructor. That is my final grade. So 1 to 5. I'm happy when things are about 4.5, obviously, but it's very difficult to get there. So I never get an A, basically, but there's always room for improvement. But see, these are the points where I usually spend a little bit of time and try to understand what's going on. So this is below, I mean, it's still pretty good, but it's below 4. So this is the course, helped me learn to apply material in order to improve thinking, problem solving, and decision making. Well, I think that's course dependent. Some courses do not necessarily teach you to, make decisions here. And I think we're learning dynamics and controls of these orbits via maneuvers. I don't think that's necessarily a skill that you will develop in this class. I'm okay with this one being around 3 actually. Actually, this semester it's a little higher than usually. Than what it is usually. I usually really get almost basically 3.0, which means that is in line with the other courses. It's not more challenging, and I'm okay with that. I don't need to make the class difficult just for the sake of making it difficult. I need you guys to learn something and accumulate skills if possible. Encouragement of active role in my learning. Well, I think this is person dependent, I believe. I think we give a lot of uncollected homeworks. Some of the comments, it was the same in the past. Some of the comments say, I would like to have a lot more homeworks, graded homeworks, and a lot more tests, smaller tests. But in my experience, more than 3 plus 3, you may have the other half of the class who really can't stand the idea of having a test every week. So, and so what I'm trying to get at is that I think we give you a lot of input in terms of do this, try to do this in SDK, try to do it in MATLAB. But then if you don't, if you're not proactive and you actually sit down and do it, then I don't know in which other way we could force you to do it. I've had this comment in the past, make the uncollected homeworks graded, even though you don't really grade them, you don't look at them, just people have to turn it in. But I don't know how much that will actually have people paying attention to the steps in those homeworks. The uncollected ones are for you to exercise. If you want to do them, you do them. If I give you a point just for clicking submit of whatever, your picture, I don't think it adds a lot of value. So I do believe we try to, I'm trying to give you some work to do that is fun, hopefully, but I may try to increase the number of those homeworks or, suggestions. Today I'll give you a lot of suggestions about what to do for the spring break. Okay. I have acquired the subject knowledge and skills set forth in the syllabus. We're still below 4. We'll have to pay a little bit of attention there, but I think we are on track with the topics that are outlined in the syllabus. What else is below 4 that you see here? Nothing else. Everybody seems pretty satisfied, I hope. The comments that I've seen, I don't know if we really have time to go over them. Well, thanks to those who said great class. I appreciate that. I think again the general comments are, I want more homeworks, but it's one guy probably or 2, and I don't know if the other ones agree. If I had seen that across the board, then I would think about it. But I think 3 homeworks, 3 tests, and suggestions on exercises is a good combination, unless you think otherwise. You can shape this class for the future. Only a few of you, deciding for everybody. You have to tell me. There was a comment about Oh, the quality of the videos, are they really that bad? Can you see okay when I post them?
Sometimes you can't see. I didn't say it, but
No, yeah. There's sometimes it's out of focus. Is it going out of focus?
yeah, it's out of focus. And,
But it's not the entire video that it's out of focus, right?
it's usually a few seconds. Yeah.
Okay. So, but in general, the resolution is okay.
Yeah.
Because I'm creating files that are about 500 megabytes, a little less, and to upload on YouTube. Here is fast. It's very fast. But I usually do it at home, and it's not that fast. So it takes work. So there was a comment. Someone was upset about the videos. We have a saying in Italy: "Don't look in the mouth of a gift horse." I don't know if that's equivalent in English, but this is additional work we are making. So I don't think I can do more than this, because I don't even know how I found the combination of resolution reduction from this thing that creates terabytes of files, and yeah, it's pretty involving. I watch them, so they seem okay on my computer, but let me know if some equations are not clear. I'm sure that sometimes it goes out of focus. So I think, unless there's something you want to bring up, yeah, this was another one. Homework, I would prefer that homework wasn't in MATLAB, and more like the test questions. I kind of disagree with this, because I think that if I ask someone to compute, just an example, orbital period of an elliptical orbit with same major axis A equal whatever. If I ask you to do it on a piece of paper, or you've done a homework where that's part of a million lines of code that you had to create from scratch, what is the difference? You've done it. You hopefully had to think about that equation, that single equation that you had to look up in your book and write it in MATLAB. So yeah, the homework is a lot more involving. I would rather have people who complain that the tests are very easy and the homeworks are hard, because the homeworks are take home 3 days. I do that on purpose. I want the homeworks to be harder and more involving, so that you come at the test and oh yeah, this was the beginning of that code that I've done. It's just that single line. That is really the intention, but maybe that's not how it's coming across. But I've had this comment in the past. Again, these are all anonymous, so I don't know if when a comment comes from someone who's really doing the homework or not. So it's often person dependent, but I think overall we're doing okay. I'll try to suggest a little more what to do. I can give you points for turning in the uncollected homeworks, but I think the extra credit that you can get from all kind of sources here is kind of insane already. So I think we are in good shape. But I'll try to pay attention. There's other comments about telling you what I'm going to teach that day. Just write it clearly and don't change. If I change topic, just rewrite it. Maybe I haven't done it a few times. I'll try to be more systematic. And bottom line, when a lecture is not super clear, it's because I haven't spent time preparing it as I should have. I'll be honest. I mean, sometimes I'm rushing things because I don't have time, and it does happen. I mean, you go to a test and you're not prepared as much as you want it. I still look at this as I am a student, and this is my grade, and I have to recognize when I'm not prepared enough. It does happen. There's some lectures that I've had in the past where I come and I don't have to look at my notes because I know that stuff so well that I don't make a single mistake. But for the most part, I come with notes because I don't have always the time that I want. But this is where we are. Do you have any comments? No? So since the sponsor is downstairs and I really have to go back downstairs, I want to finish that exercise for refacing. And then for the other few impulsive maneuvers that I would like to be part of this class, I really give you highlights. And then you guys over the spring break, for example, you can go study the details. I don't want to go through the derivations. It's really just trigonometry and geometry of vectors. And really, you should solve the few examples in the book by hands. Well, the solution is there. They do all the steps. Redo it if you want. And then I think a very good exercise is doing it in STK. At this point, you have Astrogator. Try to see if you can do the same thing with Astrogator. I think that's a very good exercise. So, but for the facing, actually, I keep calling it reface. But the facing maneuver, that we were looking at, we had a slightly elliptical orbit, right? And I want to leave and come back on the same orbit, but I was starting at some time t0 with a spacecraft in a position A, which was the periapsis. This is periapsis here. I don't want to introduce more letters, actually. And there was another spacecraft on the same identical orbit at 90 degrees of true anomaly. If this is periapsis, this is the true anomaly, of course. And it's ahead in the direction of motion. And we wanted to maneuver spacecraft A so that as B covers this distance from B to the periapsis, A goes a little faster and they catch up in this same position. So we said we choose to go on a slightly smaller ellipse inside, and we call that, yeah, this is trajectory 1 and this is trajectory 2. And we call the time to go from A to B TAB. And we said, well, the obvious relationship in terms of times here is that the period of the orbit 2, which is what I don't know, I have to choose this, I have to compute this, right? This is my unknown, has to be T1 minus TAB. Correct? Why do I have to find that? Well, because if you find the period, then you will just find the same major axis by the relationship between the two, and then you can finally do the two burns. And the two burns are equal and opposite. The first one, if I go inside, will slow down my spacecraft. So the first one is a retrofire, right? The first step is retrofire, whatever engine you have, that can give you an impulsive maneuver. And then the second one is forward. That is basically correcting, once you've gone one orbit on 2, you're just re-putting that delta V back in. You just go back to the same exact orbit, okay? So you basically have to compute one delta V, just multiply times 2 once you're done. And so the next steps, well, let's keep in mind the relationship between T and A. Let's see. Once we have T2, A2 will be given by this relationship, T2 square root of mu over 2 pi 2 over 3. This is just one of Kepler's laws as we've seen in the past. And so the first step was, well, how do you compute TAB? Because that's really what I want to be able to find T2. T1 was all the data here was given, right? I think this distance was given, this distance was given. Let's see the values. 6,800 kilometers here, radius, and this other one was 13,600 kilometers. And so the same major axis of this was found. And the period, I don't think I have the number, but you can... Oh yeah, I do. So T1 was 10,252 seconds. I think we got to that point. You just write sec just in case. Okay. All right. So by TAB, I don't know what that is yet. We said we just look at Kepler's equation. It's T1 over 2 pi. That multiplies the eccentric anomaly at B minus the eccentricity of orbit 1 sine the eccentric anomaly at B. And this was also computed. So this was T1. E1 was, I didn't give names to those points. Let's call this, that's B, this is C, right? What did we say? You can apply this, RC minus RA over RC plus RA, right? That's one way to compute your eccentricity. And that was 0.3333, whatever. Okay. So that's known, the true anomaly. So how do you get to this? I don't have the eccentric anomaly yet, but I know that the true anomaly at the point B is pi over 2. You go from this to this expression that we have seen with our proof, 2 arctangent of square root of 1 minus E1 over 1 plus E1, and here you have the tangent of theta b over 2. So you compute this, and you get the eccentric anomaly EB is 1.2310 radians. So that's the eccentric anomaly, remember the definition, at this location that I need in that equation to find AB, TAB, which ends up being 1,495.7, if you want to be precise, seconds. So I have it. Kepler's equation. Okay? Just let's highlight what I'm using here. This is the one we can solve in one way analytically, like we're doing now. When true anomaly is given, you want to find time. But when time is given and you want to find the true anomaly, you have to do the F-solve, right? One of your uncollected homeworks. Okay, so with this, you can go back and finally, second step here is T2 is T1 minus TAB, which is going to be 8,756.3 seconds, which gives you a semi-major axis from that expression up there that is 9,182.1 kilometers, which I hope is less than this. I think it is. Should be. Well, once you have the same major axis, it's the end of the story. You go back, it's basically a Hohmann transfer done twice in the same location. The velocity of A on trajectory 1 is what? Square root of 2 mu square root of 1 over RA minus 1 over twice the same major axis of that ellipse, while the velocity A to be on 2 is a similar expression with the different same major axis. And we know this, just as a sanity check, that this same major axis is smaller than this one. So I'm subtracting a bigger number here, so this VA2 has to be smaller, which makes sense. I'm going to a smaller closed orbit, less energy. I am in the same position in A, and all of a sudden I change velocity to go to a smaller energy orbit, which means I have to remove velocity if I don't change the position, right? Because again, E is V squared over 2 minus mu over R. With impulsive maneuvers, you don't change this, you only change this. And so if you plug in the numbers, I'm just going to give you the delta V, the first one, which then you double, is a negative one, if you really want to put it that way, 24851 kilometers per second. So this is the retro fire. And then the other one is just going to be exactly the same, plus, meaning that you're going to accelerate. But the total delta V, if you have a desire to estimate fuel consumption, you will have to take the modules of this. Don't keep the signs, because it doesn't matter which direction you're firing a thruster. So you add all the positive delta V's, okay? The absolute values. Okay, now there is another note to make here about phasing maneuvers. This is not the only way. You can redo this exercise by yourself. First of all, you can do this in SDK. This exact example, try to reproduce it in SDK with Astrogator. You can go to a bigger orbit where the first firing is actually accelerating, the second one is slowing you down, of course. And there is also a way to save fuel, which is waiting longer, as always. Every impulsive maneuver, every maneuver really in general, every time you use control, if you have more time, you can save on the control effort, right? So what if instead of allowing B to go one time from here to A and this spacecraft to go one time on the inside orbit, I let it go several times? That will probably save me fuel, which means that the inner ellipse, if I just look at what we just done, is getting closer and closer to the original one. And as you get closer and closer, you almost, on top of it, but you just slightly smaller. What you're doing is you're changing your same major axis, not very much, which means that in the end your delta V is reduced. There is one expression that the book just gives you, which is the following. You could reduce the delta V by doing this. Divide the time that it takes to go from A to B by the number of times you want to go on the number of revolutions you're fine with on those two orbits. Now, the most general approach that you could have, that I've actually seen in the aerospace design class last semester, so this student in particular was in Astro, and I didn't mention anything about this, but he just, I think he found it in another book. You could in general do this. You choose how many times you want to go on the original one and how many times you want to go on the one that you have to find. They don't have to be the same, and then solve, this equation with n and m are given. But in general, what is going to happen is that to make this equation an equality, your delta V is not going to be that small. You may end up finding, say that you want to go twice on this orbit and 4 times on this one. You will probably come up with an orbit that is actually a lot smaller, so you go 4 times, and that will require more delta V. So really, the way people do it, because this will be just more complicated than it should be, is you just go with this. And you can try. So basically solve this problem where instead of waiting 1 revolution on orbit 2, you make it a little bit bigger so you can go over, 3 times. And by dividing, so this TAB has not changed, of course, right? That's what it is my time to go from A to B. But this number will be reduced, which means the difference between these two is less, which means, again, you're almost making them the same orbit. You're just going a little bit faster, but it's going to take several revolutions to catch up. And if you have time to wait, your delta V will go down. Make sense? Okay, now, the maneuvers that I would like to briefly touch on, because at this point, impulsive maneuvers should be something you can handle pretty well. It is, in the end, computing a change of a vector so that you obtain a modification of the shape of the orbit, of the size, or, for example, the line of ups. So, line of ups rotation is another maneuver that you could be interested in. Now these may change shape and orientation of the orbit still in the orbital plane, or just the rotation, just the orientation of the orbit without changing at all its shape. But so I'm going to try to draw this. The book has a much better drawing, but I don't have my laptop. So say that you are on some generic closed elliptical orbit. The Earth is right there. But you don't like that. You want to change. This is the original line of ups. Let's call it L1. You want to rotate that and maybe even change the shape. So I'll just make it generic. You end up with a new orbit. And you can prove to yourself that you really have 2 points of intersection in general. When you choose 2 elliptical orbits with different same major axes, you can check that. So say that this is my start, and this is the new line of ups. This is my goal. Okay. Nothing is really said about these 2 orbits. It's just 2 different orbits with different line of ups. But what I'm focusing on is these points of intersection, I and J. Because those are the only points where you can do a maneuver. Do we understand why? Because these are impulsive maneuvers. Impulsive maneuvers only occur if you're going from an orbit to another where those orbits touch each other. Because I'm not changing the position. I cannot do it here. There's no touching the other orbit. I can't do an impulsive maneuver. I can do a continuous maneuver maybe, but not an impulsive one. So to solve for the delta V that now is not in general a Hohmann transfer, because on the original orbit I'm flying this way, On the new one, I'm flying this way, so now I have to change magnitude and direction probably. There's a few steps, and I am not going to demonstrate anything because you can look them up in the book. They're just a few steps. It's all trigonometry. I'll just give you what you have to do, which is probably pretty intuitive. Well, you have to figure out what those two velocities are, right? I'll zoom in what's going on there. You have, and of course you can do it here or here. Depends on what is less expensive. If you have time to wait to get to point J, it's always the same story. It's always a trade-off. So if that's my point I am looking at velocity on the orbit 1. I want to make sure that I use the same. Yeah. And actually, let's call this V2. Why not? I have the same sketch here. And V1, you have these two vectors. And this is going, well, they're supposed to be tangent. I'm sorry about that. Let's do it again. Okay, so you have the orbit, one orbit, another orbit. Say that this is V1, and this is V2. Okay? They have to be tangent to their orbits. Well, you want to figure out exactly what these vectors are, and then eventually figure out the delta V that you need to apply to go from 1 to 2, for example, or 2 to 1. Make sense? Okay. Well, these are the steps. The first thing you do is you notice that, again, being an impulsive maneuver, you do it when they intersect. So you set up an equation like this. Position on orbit 1 at point I, for example, or at point J, you find both solutions at the same time, has to be equal to the position on orbit 2 at point I or J. If you call the angle between the two lines of ups, eta, for example, you are given that, and you call true anomaly on the first orbit, you call it theta 1, and true anomaly on the second orbit, you call it theta 2. All right. The first thing you need to do is finding these true anomalies. Given, so this is given. Okay. You need to find theta 1 and theta 2, one of the two, because they are obviously related to each other. All right. You know that theta 2 is equal to theta 1 minus theta. So the way you find theta 1 is by imposing this equation, and after a few steps, you believe me on this, you can easily see the steps on the book if you want to. This is your solution for the 2 points. This is an arc cosine of C over A cosine of phi, where phi is the arctangent of B over A, and I have to give you these A, B, and C. A is eccentricity of orbit 1, angular momentum of orbit 2 squared, minus, I know this looks ugly, but it's really not. Not a huge computation to obtain these, to prove these expressions. Sine of eta, C equals h1 squared minus h2 squared. All this is originating from writing the Keplerian equation for R1 and R2. For example, R1 is going to be h1 squared over mu 1 over 1 plus e1 cosine of theta 1. And this other one obviously will be h2 squared over mu 1 over 1 plus e2 cosine of theta 2. So you start from this equation, you use this expression, you use the cosine subtraction formula, you call those constants that way. In the end, that's what you get. It's just a few steps. There's nothing special. It's trigonometry. But you can find the intersection point, the true anomaly at the intersection point. Once someone has given you the fact that they want to change the line of ops by an angle theta. Now let's go back to this one here. That's the important one, because that is the sketch I use to find the delta V. We have called this little angle here the direction of velocity v2 with respect to the normal direction. We call that flight path angle, for example, gamma 2, right? While for the other one, I have gamma 1, right? Have we done that? Down there. Did we say if we look at the normal direction at any location of the satellite, this is your flight path angle, right? Well, you do the following steps. One, you look at the first orbit, and you know that the velocity, the normal component of the velocity, we've seen all this stuff, is h1 over r. Now r is in common again, is this one. You know that the radial velocity is equal to this other expression. At this point you know what theta 1 is. And you finally compute the flight path angle for this one. And the flight path angle is measured with respect to the local perpendicular to the position vector, right? Which is in common. So I just don't want to confuse this sketch even more, but really if that's gamma 2, this is gamma 1, right? Agree? And so you can repeat this for the other orbit. And you finally have your way of computing that delta V. How would you compute these vectors that connects the two? Any ideas? I have the magnitudes of those velocities at this point, right? Because if you have computed these two quantities here, your velocity 1 is clearly square root of V perpendicular 1 squared plus V radial 1 squared, and the same for the other one. So you do know the magnitude of those velocities. You also know their orientation with respect to a common line, because this is really what's happening. You have, let's try to do it the same way. This is the common line, which is the normal to the radius, and you have gamma 2 here, and that's V2. All right, and then you have V1 maybe up here, and this angle is gamma 1. So you have this triangle here. How do you find out what this is? If you have two sides of a triangle, A, B, and the angle between the two alpha, how do you find C? Right? Isn't this the one? So I'm going to do the same there, where instead of C, I'm trying to find the delta V, really, right here. I care about the magnitude. The delta V is going to be square root of v1 squared plus v2 squared minus 2v1, v2. What angle do I put in here? Gamma 1 minus gamma 2, right? And that's the end of the story. So this maneuver is kind of involving. You have to find, with those solutions that I removed, the true anomaly, theta 1, which means that you're going to find theta 2 as well, where the orbits intersect. Once you found that, you have r, once and for all. You do have this distance from the Kepler's equation. Keplerian expression for an orbit. Then you go and figure out the velocities, normal, radial, the flight path angles, and you can use this information to get your delta V. And that's the end. And this is really, in general, this was done for changing the line of ups. But in general, if you have intersection of two orbits where the velocities are completely different in the same plane, of course we're doing everything in the same plane for now, but if you have V2, V1, they're completely different. Here I haven't made any assumptions. That's what you will have to do. How do I go from orbit 1 to orbit 2 at the point of intersection? Figure out what that point is, compute the velocities, and close the triangle. Make sense? Any questions on this? I skipped the steps that basically give you the theta 1 solution, but again, it's really not that interesting. Okay. So try to solve these as well in STK. There is an example on the book that you can reproduce in STK, or you can just take an elliptical orbit like the one that we had when we did Oman transfer, and just don't even change anything. Same major axis or eccentricity. Try to see if Astrogator can find a way to change the line of ups in the same plane. This is something you may need to do for Molniya orbits, for example, where, as you may recall, the apogee has to be pointing in a certain, the line of ups has to be pointing in a certain way in space to look down at some location. No questions? So the last thing that I wish to cover, there's more stuff in the book about impulsive maneuvers, but I think these are giving us a pretty good idea of how these are computed, is plane changes. Finally, we do something out of plane. Okay? And again, if I had the book, it would be much better because I would project something. I'll try to sketch two different planes that intersect and the orbits on them. So we'll see what happens. I don't like that it's that high already. Okay, start down here. Okay, so I have certain plane here with my orbit line on it. This is the portion of the orbit that we can see. Okay? But then there is also another plane that I want to go to that it's up here. So I am on plane 1, and I want to go, for example, on plane 2. So I want to go from this orbit to this one. Is it clear at all? Probably not. Oh. Does it make sense what I'm doing? Without the orbits. You have two planes that intersect in a line. This one continues behind. This one continues down here. So whatever is happening on these two planes, if I need to change from a plane to another, it has to happen where the orbits, again, intersect. So this ugliness, if you look at from the line where they intersect, really this is the line where the two planes intersect, there is actually the common UR line. If you look from this direction, this is what you see. Plane 1, plane 2, the common UR direction, And here you would have the u perpendicular direction for orbit 1. And here you have the u perpendicular direction for orbit 2. Does it make a little more sense? So my satellite was maybe orbiting inside orbit 1, and at some point I decide that I have to go to orbit 2, and I change the velocity somehow to go to this other plane. So I now add a delta v that is not in the same plane of the orbit as I've done so far. Okay. This is genetic. I'm not saying anything about orbit 1 or orbit 2. These terrible sketch here, they definitely have to intersect somewhere. Maybe here. They don't have to necessarily intersect on the other side. If this is, I don't know, periapsis, they don't have to touch each other at apoapsis. But one point has to be in common, again, because we're doing impulsive maneuvers. Okay, well, the delta v in general as a vector is going to be v2 minus v1. That is v r2 minus v r1 on u r1, for example. It's in common. Plus v perpendicular 2, u perpendicular 2, minus v perpendicular 1, u perpendicular 1. All right, I care about magnitudes, really. That's what I'm doing here. The delta v in magnitude is going to be delta v dotted with delta v. Well, this is squared, but you can take the square root if you want. Well, these are three vectors. So let's call this angle delta. Of course, this will be a given as well. Well, what is this? It's VR2 minus VR1 squared. Make sense? I am dotting this vector with itself. So UR1 dotted with UR1 is 1. Plus V perpendicular 1 squared plus V perpendicular 2 squared plus, you get this extra term, 2, V perpendicular 1, V perpendicular 2. That is multiplying this dot product of the two different perpendicular directions that I have. And just to make it quick, this one is equivalent to minus 2 V perpendicular 1, V perpendicular 2 cosine of delta. Okay. Well then, the genetic delta V will be the square root of all that. And we can comment on this. What would you do if you were asked to change? Sorry, thank you. So what would you do if someone told you you need to change plane? You were, well, this could be the start orbit. The fact that it's horizontal doesn't mean anything, but this could be the equatorial plane. And you want to get there because you are a geostationary satellite, but you didn't launch from the equator, so you are stuck in some other inclination. You need to change the plane so you know how much delta you have. That's a given. And now you look at this, and you start thinking about the cost of this maneuver. You would like to drive everything that is under the square root to the minimum that is possible, right? Okay. What would you do? You have choices here on when to do the maneuver. Where? The first thing is that no one does this. You don't change the radial component. That's your choice. So whatever you do with your delta V, you don't add or remove anything to whatever is the velocity there when you start to perform the maneuver. Okay. What next? You would like to keep these guys to be as low as possible. So usually you do it at apoapsis. So one is VR2, basically you just leave it, you just leave these alone. 2 is do it at apoapsis. Apoapsis. All right. And that's the rule of thumb. Now, if the two apoapses overlap, because there's no guarantee that they overlap, it depends on what is your goal orbit. But if they do, then those V perpendicular are what? What happens at the apoapsis? Or at the periapsis? Do you have any V radial? There's no V radial, right? It's all V, so that basically just becomes V1 squared plus V2 squared minus 2V1 V2 cosine of delta. Also, that is one case. This is case A. Case B, which is also very common, if V1 is also equal to V2, this expression takes this form 2V sine of delta over 2. You can easily prove it to yourself. And that basically means that you're just purely taking the velocity vector, whatever it is at apoapsis, you just change its direction, you don't change anything else. You just make it perform a rotation of an angle delta, but you don't change its magnitude, you don't change anything else other than the plane. So this is a pure plane change maneuver, really, or change of inclination if you want, where basically your orbit looked like whatever it was at the beginning, you just change the plane, nothing else. It remains exactly the same. Same major axis, eccentricity. You haven't changed the velocity really in magnitude, only its direction in space. Make sense? And so your energy equation remains exactly the same, your shape as a consequence. The only thing that changes is the h vector, which way is pointing. You know, all the three-dimensional quantities can change, but not the whatever is in the plane remains the same. So just to give an idea, this is a very expensive maneuver. If you are, and we're done here, at 7 kilometers per second, start doing the math with different angles and see how expensive this is to change just a few degrees. What is the sine of 0? 0. If you start going up, you can approximate this to be almost equal to delta over 2, so it's a small number, but still is multiplying twice your orbital velocity. As I think I mentioned in the past, the space shuttle had the capability of changing its inclination just a couple of degrees, because it was flying actually faster than this, a little faster than that. So it's a very expensive maneuver. I know I rushed this, I know it was quick. I really invite you to look at the book for the steps, the detailed steps on how to get these delta V's, but this is how you get them. Solve the exercises on the book and try to solve them in STK, which is, I think, a lot more entertaining, because you can see in 3D what's going on, the different colors, and we're out of time. I wish you a good break. Thank you.